Let me show you how to be a good Bayesian.
In this episode, I'm thrilled to welcome Tom Griffiths, one of the most influential figures in computational cognitive science. Tom is the Henry Luce Professor at Princeton University, where he bridges the fields of psychology and computer science to study how humans, and increasingly machines, learn, think, and make decisions. He's also the co-author of the best-selling book Algorithms to Live By, and the recent one, Bayesian Models of Cognition, Reverse Engineering the Mind. In our conversation, Tom walks us through how Bayesian models can help us understand the foundations of human intelligence, from how we form inductive inferences to how our cognitive processes differ from those of modern AI systems. We dive into the idea of humans as noisy Bayesian agents, the importance of prior elicitation in psychology, and why individual responses may sometimes offer more insight than the averaged wisdom of crowds. We'll also talk about the tension and potential synergy between human and machine intelligence. Tom shares his thoughts on generative AI, representational alignment, and what it will take for artificial systems to truly complement human reasoning and values. And as always, we end with practical advice for researchers entering the field and a peek into Tom's future work. This is Learning Bayesian Statistics, episode 132, recorded December 18, 2024.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PIMC Labs can help bring them to life. Check us out at pimc-labs.com.
Hello, my dear Bayesians. Do you remember Hugo Bern-Anderson? Of course you do. He was in episode 122 of the podcast, and we talked about learning and teaching in the age of AI. And that's because, well, Hugo is not only a friend of the show, he's also an independent and brilliant AI and data scientist at Vanishing Gradients. And he just dropped a new episode of his podcast, High Signal, with Fai Li. They talk about the rise of foundation models, what human-centered AI means in real systems like elder care and education, and why spatial intelligence might be the next big shift beyond LLMs. Honestly, it's a wide-ranging conversation. It's a thoughtful conversation on how AI is reshaping society and how we can shape it back. It's definitely worth a listen, so I wanted to highlight it here in case you want to check it out. Of course, the link is in the show notes. Okay, on with the show now. Tom Griffiths, welcome to Learning Bayesian Statistics.
Hi, great to be here.
Yeah, thank you so much for taking the time. I know you're very busy, and that was hard to find a slot in your schedule for that one, but thank you so much. I'm very grateful and very happy to have you on the show. Before we talk about all the amazing work you do on the neuroscience side, maybe can you tell our listeners basically what you're doing nowadays and how you ended up working on these?
Yeah, so I'm a computational cognitive scientist. What that means is trying to understand the mathematical principles behind intelligence. And the way that I do that is by thinking about the abstract computational problems that human minds have to solve, what the ideal solutions to those problems look like, and then how we can use those solutions to better understand human behavior. And so for the kinds of problems that I'm interested in, there are things like learning, inference, problems for which Bayesian statistics is particularly useful, as well as all sorts of other ideas that come from computer science, machine learning, and AI. And so for that reason, we use these methods extensively as a kind of standard against which we can compare human cognition, but also taking human cognition and the amazing things that people do as a source of insights about ways that we can improve our current approaches to statistical learning.
Yeah, so I am guessing that to do that, you are using at least sometimes some Bayesian statistics, are you?
Yeah, so one way of thinking about Bayes' rule is that it's really a theory of inductive inference, right? So if you learn Bayes' rule in a probability class, you just sort of learn it as a tautology of probability theory. And if you learn it in a statistics class, you learn it as an alternative way of thinking about how to perform inference. But if you learn it in a cognitive science class, you learn it as a theory of how it is that we go from limited data to conclusions about uncertain hypotheses. And that's really fundamental to understanding things that people do. So one of the big projects of cognitive science is trying to understand how people are able to learn so much from so little. We learn language from just a few years of exposure. We can learn new concepts and new words from just a single example. How is it that we make those kinds of inductive leaps? The best way to understand that is in terms of the inductive biases that people bring to the learning problems that they solve, right? The things other than the data that allow them to draw particular conclusions. And Bayes' rule allows us to formulate those inductive biases in terms of prior distributions and sort of structured hypotheses that those distributions are defined over in a way that allows us to then explain these aspects of human cognition.
Okay, yeah, I see. And so we'll definitely get back to that, but first, just to dive a bit deeper into your background, do you remember when you were first exposed actually to Bayesian statistics?
Yeah, so my undergraduate degree is in psychology, and basically what happened was I was a student in Australia. I grew up in Perth in Western Australia, and in high school, actually, you get to learn some statistics. So, I took math classes and learned probability theory and some, linear regression, a lot of like basic statistics in high school. And then when I was going to university, the way that it works there is you have to choose what degree you want to do in your last year of high school. And so they were like, do you want to be a lawyer? Do you want to be a doctor? Do you want to be a scientist? These were all of the options. And I was like, I really don't know what I want to do. I just want to learn things that I haven't had the chance to learn about. So I ended up enrolling in a Bachelor of Arts degree and choosing to study stuff that I just not had the chance to get exposed to in high school, like, psychology, anthropology, philosophy, ancient history. And every year you had to cut one of those out, and you got more and more focused. And so the one that I found the sort of most rewarding was the psychology one. And so that's the track that I was on. And so when you learn psychology, part of what you learn is statistics, right? You take these classes, and for most psychology majors, they're the worst classes in psychology. They're the ones that everyone dreads. And for me, they were some of the most exciting classes because they were really about taking those kinds of mathematical ideas that I'd already learned a lot about and using them to really understand the world. And so it was through those psychology statistics classes that I first learned about the idea of Bayesian statistics and Bayes' rule and so on. The way that you learn statistics in psychology is much more kind of like being told, in this situation, you use this kind of hypothesis test. And, in this situation, you run this kind of analysis. And I was always sitting in the back of the class and thinking, well, why is that what you do in that situation? And why is that the kind of hypothesis test you use or the kind of analysis you run? And trying to work out from sort of mathematical first principles why these are the things that you should be doing. And that was actually a really good way of learning statistics because it sort of forced me to rediscover a lot of these things that if I'd just been in a class and they were fed to me wouldn't have been as exciting. And so I enjoyed the Bayesian perspective as a way of really kind of like making sense of a bunch of things that were perhaps, like harder to understand in the context of classical statistics.
Yeah. So it's like, it sounds like it's really it's almost you who went into the Bayesian stats framework and not the Bayesian stats that were imposed on you by some course, right? Because you were asking the questions of, okay, but how come we're doing that in this case and not these? Which I can definitely relate to. That's also why I always had frequentity stats has always been extremely hard for me to learn, because I don't have a brain that works in the way that is remembering, in this case you do that, in this case you do that. I am much better at remembering the process and the reasons behind why I do something, whereas just, without understanding why, doing something. And so the zoo of statistical tests has always been a nightmare for me, because I could never remember. Whereas if you learn from first principles in a generative process like you have to do in the Bayesian framework, that just works way better for my brain, for instance. And it seems to have been the same for you.
Yeah, I mean, I think one of the things that, I got out of learning in the way that I did was having a kind of like solid basis in frequentist statistics, and, having had that already established, so that then when I encountered Bayesian statistics, it wasn't like I was able to be more charitable in the way that I think about frequent statistics. And I still use a lot of frequent statistics when I write psychology papers, because that's really the language that community uses, right? And the way that I think about it is, via the sort of Neyman-Pearson interpretation, something that you can think about as a way of approximating the kind of inferences that you might make in a Bayesian setting, right? So you can think about what a lot of classical frequentist hypothesis tests are doing is measuring something like a unit of evidence in a way where you're doing that approximately, and you have to sort of correct for the approximations via the kinds of methods that frequentist statisticians developed. And so that was a way that I could integrate that classical background with the perspective on statistics that I got from thinking in that Bayesian way. But I think it's also interesting to draw a distinction between what you're trying to do as a statistician and what human brains are trying to do, right? So as a statistician, you're trying to convince another person that they should draw a conclusion from the data that's the conclusion that you're drawing from the data. And all of the controversy about prior distributions and all of the stuff that kind of informed that classical frequentist versus Bayesian debate, that's in the context of that sort of question of how do you make that argument, how do you be objective in making that argument, how do you construct evidence which is compelling for another person. In the context of cognitive science, I feel like there's just much less controversy around thinking in a Bayesian way. And part of the reason for that is that all of that subjective stuff is intrinsic to the thing that a human being is doing when they're making an inference, right? So if I'm using Bayes' rule to explain how you walk around the world and see data and interpret those data and learn things from them, then the part of that which is about your prior distributions and all of the subjective stuff which Bayes' rule allows us to talk about, that's actually fundamental to it. It's not something which is an obstacle to, objectivity is not what you want there. Subjectivity is exactly the thing which is going on, and we want to be able to capture the content of those subjective beliefs. And so for that reason, I just feel like it's a really good fit for the problem that cognitive scientists have to solve.
Okay, yeah. I was going to ask you basically now, so how does that work for the brain and things like that? So maybe to dive into what you're doing, can you tell us how you actually develop these statistical and mathematical models of higher level cognition? Yeah,
so our starting point is always thinking about the abstract problem that human minds have to solve. So there's a cognitive scientist whose name was David Marr, and he introduced this idea of there being 3 different levels at which you can analyze a information processing system. So the first level, the most abstract one, is what he called the computational level. And that's really just saying, what is the problem that the system is solving and what's the ideal solution to that problem? And then the level below that is the algorithmic level, and this is what are the actual processes that are being executed? What are the representations and algorithms that are approximating that ideal solution? And this is kind of like, for psychology, this is kind of like the classic level of cognitive psychology, where we're trying to figure out what are the sorts of heuristics that people might use, what are the elements of memory and similarity and attention that are all combining together to allow us to answer a question. And then below that is the implementation level, and this is the level at which those representations and algorithms are implemented in some kind of physical substrate, right? And that's like in the, the case of understanding people, that's the domain of neuroscience, trying to figure out how representations and algorithms are instantiated in brains, built out of neurons and so on. And so when we're making Bayesian models of cognition, we typically are operating at that abstract computational level, where we say, what is the problem that the human mind is solving here? And when you're thinking about an inductive problem, right, where you've got some data and some hypotheses you want to evaluate, and you don't have enough data to tell you which hypothesis is the right one, then that's a setting where, thinking in Bayesian terms is actually the way to characterize what an optimal solution to that problem might look like. And then the next step is saying clearly, what is the data that people get to see, and what are the hypotheses that they might be evaluating? And one way to do that in a Bayesian way is to think about the generative process that's involved, right? So how are the data generated? What's the sort of, the sequence of steps that underlies those data being generated? What are the latent variables involved? What's the structure that people are potentially inferring from the data that they see? And so that gives us a way of then conceptualizing the problem, and then we can make some guesses about what a sort of prior distribution might be that would be an appropriate prior distribution for those structures. And we can then get a model that we can compare against human behavior. And then we can also, do some iteration and try and figure out, okay, well, just using this kind of model, is there a way that we can infer what the prior distributions are that people might use? So I can give you some concrete examples. So this idea of trying to understand human cognition in terms of probability theory, at the time when we were doing our initial work in this area, and this is work that I was doing as a graduate student working with Josh Tenenbaum, we were really sort of up against this idea that people are really bad at thinking in terms of probabilities, right? So the sort of Daniel Kahneman, Amos Tversky had run this set of experiments documented in the book Thinking Fast and Slow, right, which sort of suggest if you give people a problem that's a Bayesian inference problem, they're not going to do a good job of solving it. And so what we wanted to do was say, actually, look, there's a different way of thinking about how we use probability theory here, where their focus had been on people's intuitive reasoning about probabilities. What we were interested in was using probability theory just to characterize the problems that people were solving, but never actually asking them anything which is a question about probability, right? It's very clear that people have sort of messed up conceptions of what probabilities are. And if you ask them to do a probability problem, they sort of treat it as a math problem, they do the math wrong, and they just have sort of like wrong ideas about the way that probability works. If you don't say anything about probability, and you just give them a problem of inductive inference, you can analyze the answers that they give in terms that, probability theory is the right tool for analyzing how to solve that problem, and it can give us insight into their answers. And so we took a set of different domains where you could frame a problem we call a predicting the future problem. And this problem is, given that you observed some amount of a quantity, what will the total amount of that quantity be, right? So an example of this would be like, I tell you a movie has made $90 million so far. What would you guess for the total amount of money that the movie is going to make? I'll ask you, Alex, this question. What's your guess for the total amount of money that this movie is going to make?
Okay, so it's made $99 million, you said?
90 million so far.
90 million so far. In how long?
You don't know. You just hear on the radio.
Okay. Okay. So I don't know. The movie has made 99 so far, and I have to guess what the total will be without knowing for how long the movie has been out in the theaters. Okay. Well, then I would say 125.
Okay. All right. And now you hear a movie's made $6 million so far, what's your guess for how much money it's going to make?
6.7.
Okay. All right. And now, if you meet a man in the street and he's 90 years old, what would you guess for his total lifespan?
90 years old. How long is he gonna live? Oh, that's a tough one. I think for me it's tougher than the movie. I would say 92.
Great. Okay. And then you meet a 6-year-old boy. What would you guess for his lifespan?
So let's say this is where I live right now. So rich country. I'm guessing that the average expectancy is like 80 something for men. So let's say 81.
Great. Okay. So I gave you in those examples the same numbers, right? But the answers you gave me were different. So you gave me a higher number when it was about, for the $90 million movie, you said 125. For the 90-year-old man, you said 92. And you gave me, so it was a higher number for the movie. But then when I asked you about the $6 million movie, you said 6.7. And for the 6-year-old boy, you said 81. So you gave me a lower number for the movie in that case, right? Why did that happen? Well, the obvious answer is because you have different prior distributions that you associate with those quantities. And in fact, what we showed was that if you just ask people questions like this, you can very easily elicit these implicit prior distributions that people are using when they're solving these kinds of problems. And so the grosses of movies actually follow something like a power law distribution. So the answer you produce should always be a multiple of the amount that you saw so far. And human lifespans follow roughly a Gaussian distribution. So the amount that you predict is basically something like the mean until you get close to the mean, and then you predict something which is a little bit longer than what you've seen so far, which is exactly what you did. So people, even not the podcasters who know a lot of Bayesian statistics, but just everyday people have exactly those intuitions, and we can show that across all sorts of different kinds of things: the length of poems, how long people will serve in the House of Representatives, all of these kinds of everyday quantities that people have some familiarity with. They're able to make these judgments about in a way that reflects the fact that they have implicit prior distributions that they're using. So that's a sort of simple example. When we make these Bayesian models, the hypotheses that are involved can be much more complicated. They can be entire causal structures, or hypotheses about what the meaning of a word is, or things that are far more complex than this. But this is one of the first studies that we did where we really said, hey, look, here's a tool that you can use that tells us something about what's going on when people make these uncertain inferences.
Yeah, this is so. First, thank you, because that was very fun. I love it when we do experiments like that on the podcast. I love that. And yeah, I mean, I'm really surprised to hear, and a good surprise that people have these intuitions even when they don't have daily exposure to statistics and distributions. That's great, because that's something I'm definitely gonna use next time. I talk about my job, and because when people ask me what I do for a living, if I want the conversation to end, because I don't want to talk about that right now, I say I'm a statistician, and then that's fine. Then people will close and be like, oh my god, I hate math, or I was so bad at stats. With that thinking that you have to be extremely to be good at stat or math, you have to be gifted, and if you're not, then you're done. If I want the conversation to continue, I'll say I'll do something like, I ask them if they have seen Moneyball, the movie Moneyball, and then they ask me, oh really, so what do you do, blah blah. But then I'm definitely gonna use your example to prove to them that they have actually intuitions about stats, and it's not that complicated, and as a lot of things, it's just a lot of training and sweat and tears to get good at it. But yeah, I love that. That's really fascinating. And that reminds me of a modeling webinar I did on the show with Justin Boyce, who is statistics professor at Caltech. And one of the methods he uses for not only eliciting the priors, but then refining the priors that people give is that, so for instance, the questions you gave me, then he would ask people, would you bet your house that this is the true answer? And if they don't, then that means they actually have a prior that they can refine. And when we get to the number that they would bet their house on, that means, okay, here they are like pretty sure about their prior. And I find that's a great method to use to ask priors to people who don't really know stats, but I need their input, for instance, from my model. That's a great method. I don't know if you've seen something like that in your research or not.
Yeah, so a lot of the work that we've done that's kind of like related to elicitation has really been around finding tasks that allow us to get information about implicit probability distributions that might go beyond the kinds of settings where traditional elicitation methods are used. So, one of the challenges for elicitation, if you're doing something like asking people about quantiles or these other kinds of things, is that those methods work quite well for a single dimensional quantity, but they don't scale to, so like how do you define a prior distribution over abstract objects, or how do you define a prior distribution over quantities that have, many, many dimensions? And those are the kinds of things that as cognitive scientists we're often interested in. So one of the weird things that we've done to try and solve that problem is doing things like running Markov chain Monte Carlo algorithms with humans. So in your Markov chain Monte Carlo algorithm, you set up a Markov chain where you sample from a sequence of probability distributions where each distribution depends on the previously sampled value, and that sampling process is normally done by a computer, right? And that's the way that you're getting the relevant probabilities. What we do is we run exactly the same kinds of algorithms, but where the sampling process is implemented by a human being. So when people answer a question like the one that I asked you, they don't always give you the same answer. You actually get a lot of stochasticity in the answers that people give. And in some other work, we've shown that, in fact, that stochasticity often reflects what the underlying posterior distribution is. So if you ask people questions like the one that I asked you, and we actually calculate the posterior distribution using the appropriate prior, and we plot the posterior distribution against the distribution of responses, we get something which is basically like a nice linear plot on a quantile plot. And so what that suggests is that we can use people as random number generators, and then we can define algorithms that are using those people as a means of then sampling from distributions that are associated with the way in which they're answering that question. So we've done this in a few different ways. One of those ways is something called iterated learning. And this is an idea that comes from the language evolution literature, where if you think about how you learn language, you learned language from somebody who learned language from somebody who learned language from somebody who learned language, right? And so if you think about what that process is, if you just think about this as now there's a chain of individual learners where each learner is learning from the utterances that are produced by the previous learner, you can think about that as a Markov chain. You have a learner generates some utterances. The next learner learns from those utterances, generates some utterances based on what they learn. And if you now think about that from a Bayesian perspective, you have a learner who sees some data, forms a posterior distribution. If they sample a hypothesis from that posterior distribution and then sample data from the hypothesis that they chose from the sort of corresponding likelihood function, then the next person sees those data, samples computes a posterior distribution, samples a hypothesis from that posterior distribution, generates data from the corresponding likelihood function. That defines a Gibbs sampler. And that Gibbs sampler, the stationary distribution of that process, is the prior distribution that's used by the learners, assuming all of the learners have the same prior distribution. So what that means is any situation where you have these kinds of games of telephone, where someone is like making an inference from data that was generated by a previous person, the expectation you should have is that process is going to converge to the prior distribution that the agents are using when they're making those inferences. And so we can set that up in the lab for this predicting the future problem that I told you about. an easy way to do this is you just get people to generate their answers, and then for the next number that I give you, right? So I told you the movie had made $90 million so far. So the next number that I would give to the next person would be, I take your answer of 125, and I would sample a number uniformly from between 1 and 125, and then that would be the data that I would give to the next person. And if you iterate that, that converges to the prior. And we can use this, we sort of confirm that this works in this one-dimensional case, but we've actually used this as an elicitation method for measuring people's prior distributions on much more complicated things. Elements of language, category structures, causal relationships, all of these things are actually things that we can now sort of measure and we can use to inform the Bayesian models that we make of how people perform inductive inference.
Okay, yeah, that's really fascinating. That sounds to me like more sophisticated, more evolved wisdom of crowds. So it's like I really love that. I didn't know you could do that. That's really fascinating.
Yeah, well, I think
how? Yeah.
I just on the wisdom of crowds point. I mean, so wisdom of crowds is normally you get a bunch of people and then you average together their responses, right? And that's more accurate than the individual responses. We actually wrote a paper where we called it something like the wisdom of individuals, right? Because what this suggests is that within any individual, there's actually that whole distribution already. And so you can elicit that distribution and you can actually get a better, characterization of what's going on with that quantity than you would if you just ask that individual one question, in a way that is reminiscent of that individual, of that wisdom of crowds phenomenon. Yeah.
Yeah. And how? So, obviously, I'm curious now with the relationship with the whole generative AI research. Do you? And I know you work on that, and I recommend people take a look at your latest book, Bayesian Models of Cognition, at MIT Press, and that's in the show notes. That's a big book, 600 pages, folks. So if you like that, you're gonna have a lot of things to read. So can you tell us a bit how do you see the relationship between human cognition and artificial intelligence?
Yeah. So I'll maybe say something specific and then say something more general. So the specific thing is, yes, all of the things that we just talked about are actually things that you can do with something like a large language model, right? Like, GPT-4. So we've actually used these methods, and my postdoc, Jian Xiaozhu, has actually run experiments where he's used exactly the same paradigms that we used with people to measure what are the implicit prior distributions over things like the grosses of movies that are in GPT-4, and showing that we can actually use this iterated learning procedure with these large models, not just to pull out prior distributions, but also to get information that otherwise these models don't want to release, right? So if you actually ask them to make predictions about things like, when will there be superhuman AI? They really don't want to answer those sort of speculative questions. But if you ask them a much more concrete question, like if we create human-level AI in 2025, then what year will we generate? Will we create superhuman AI? It's actually kind of happy to answer those conditional questions, and so you can actually use that to then run one of these little Gibbs sampling procedures and get a sense of what its beliefs are about things that it might not otherwise want to tell you. So that's, these kinds of methods specifically work there. They're also related to, there was a paper in Nature earlier this year that talked about model collapse, which is if you take a generative AI model and then you train it on all of the human data, but then you generate a new data set from that and you train another AI model on that generated data set and you keep on doing that, what happens? And of course you get this result where it collapses, right? Like it sort of ends up converging to what we would say is its prior distribution. So it's exactly the same result that we had when we were trying to characterize this iterated learning process in people, which is that you get, this deterioration towards the prior. In terms of thinking about how human minds relate to AI more generally, one high-level point is that in the same way that we can think about human cognition in these Bayesian terms, it makes sense to think about these AI models in that way, right? So to the extent that these models are solving inductive problems and are doing a good job of solving those inductive problems, then Bayes is a good tool for making sense of that. And that's part of why it's reasonable to sort of ask these questions like, what are their prior distributions? We wrote a paper, this is with, papers led by Tom McCoy, and we wrote a paper called Embers of Autoregression, in which we show that, in fact, AI models like GPT-4 and other large language models are overly influenced by their prior distributions, in the sense that you can ask them questions which are completely deterministic questions, where there's sort of like only one correct answer and your prior shouldn't matter at all, and they are nonetheless influenced by the prior distribution that they've learned from looking at all of the text on the internet. So for example, if you take GPT-4 and you ask it to count how many letters appear in a string of letters, it is more likely to give you the correct answer if there are 30 letters in the string than if there are 29 letters in the string. And the reason why is because the number 30 appears on the internet more often than the number 29. And this model has been trained to predict things that are on the internet. And so it's influenced by that prior distribution when it's answering a question where the prior should be completely irrelevant. So I think, there's a productive sort of analogy that we can make in terms of using these sorts of methods to analyze these systems. By doing that, we can pull apart some of the ways in which the priors that are used by humans and AI models might be different from one another. But I think more generally, it highlights the fact that there are some fundamental differences between these kinds of systems. And those differences aren't necessarily in terms of these abstract computational level problems that we're trying to solve, right? These things that are the things that we analyze in terms of Bayesian inference. They're more at these other levels of analysis that I mentioned, in terms of the constraints that come from, that level of algorithms and representations, or the constraints that come from the way in which these systems are physically implemented. And so if you want me to talk about a more general take on humans and AI, I'm happy to do that. But in terms of the Bayesian part, I kind of think the Bayesian part is one of the things that we share. And it's the other stuff that really is where we end up with our meaningful differences.
Okay. Why is that? Do you have already some research about that? Things you can talk about?
Yeah. So the way that I think about it is that human intelligence has been shaped by a set of constraints that human minds operate under, and those constraints are quite different from the ones that are faced by intelligent machines, right? So if you think about what's characteristic of human intelligence, all of the things that we learn from the data which we're going to experience in the course of a single human lifetime, right? So that means that we're intrinsically limited in the amount of data that we can learn from, right? In order for something to be useful to you, you probably need to learn it relatively early on in that lifetime. So, realistically, we're talking about, maybe 20 years of data that you're you're using to form most of the inductive inferences that you're going to make about the world that you live in, right? And even much of that happens in the first 5 years, right? Like we learn language pretty well in the first 5 years of life. We've kind of figured out most of the causal structure of our environment, although we're still fine-tuning it after that, right? We kind of got most of the stuff that makes us a human being in those first 5 years of life. Okay, so that's thing number one, is limited data. That's something that shapes human cognition, is that you have to take about 5 years to figure out all of this stuff. The second is that we do all of that learning and all of our thinking with a fixed amount of compute, right? Which is what you're carrying around inside your head, 2 to 3 pounds of neurons, right? So that means that, way number two that we're different from our AI systems, right, is that we have to use that same amount of compute for every single problem that we solve. And so we need to be efficient in the way that we use those computational resources. We need to be able to recognize when a problem has the same kind of structure as one we've seen before. We need to be smart about how much time we spend thinking about any one particular thing. And so we need, something that allows us to make good use of those limited computational resources. So that's number two. And then number three is we have limited bandwidth for communication, right? So If it was just possible for me to transfer my brain state to you, then we could easily overcome those limits on data and computation, because I could just, share with you all of the data that I've ever seen, all of the conclusions that I've drawn from it by computing on those data. If we needed to work on a problem that was too hard for one of us to solve, we could just combine our computational resources. That would allow us to overcome those constraints. Instead, we have to do this by doing what we're doing right now, making honking noises at each other, right? And that is a really low bandwidth method of communication. So humans have developed all sorts of workarounds for this, right? We've developed language that allows us to convey complicated concepts to one another, teaching as a means of compressing information. Like all of the data that I've seen, you don't need to see, you just need to have the information from me about what to conclude from it. We develop methods for creating social institutions, things like science, that allow us as a community to aggregate knowledge across generations, engage in what's called cumulative cultural evolution. All of that stuff is stuff that allows us to, try and overcome those constraints, but it's still not as good as if we had sort of perfect high bandwidth communication. Okay, so by contrast, the current approach that's taken in AI is one of scaling the amount of data that's going into systems. So it's many, many human lifetimes of data that these systems are now trained on. It's scaling the amount of compute that's going into those systems, and you can kind of have arguments about how that compute compares to human minds, right? But the relevant thing is that that number is something that's easy to increase, whereas for humans it's not. And you have the potential for just being able to transfer states between machines directly, right? So you don't have to worry about those low bandwidth communication bottlenecks that are characteristic of human cognition. And so for that reason, we might expect that human intelligence would continue to be quite different from machine intelligence, because it would be nice to have machines that could learn from less data and be more efficient in the way that they use computational resources. But if you just want to make a machine that does a particular task, and in particular, if you want to be the first person who makes a machine that can do that, then you can kind of get around all of the hard engineering that might need to go into producing a system that has good inductive biases for solving a problem, or producing a system which is able to be resource efficient in doing that. And that's kind of the mode that we've been in for AI, is really just turning up that knob of data and compute, because it's the thing that so far has been the easiest way to get us to more effective AI systems.
Okay, and so I'm wondering, so two main things I'm wondering, so trying to order my thoughts. First one is, then if I understand correctly what you're saying, you're mainly saying that the way we're going to be able to make these generative AI learn is going to be different from the way our brains learn. Does that mean you think there is something we can do so that we build these machines, these generative AI, in a way that's complementing our learning and even helping our learning, and maybe fast tracking it in some way? What kind of potential do you see here? Also, what kind of drawbacks are you trying to maybe avoid? Because we are building these machines, so we are in a position where we can also try and avoid costs that we can anticipate.
Yeah. So I don't think there's anything intrinsic to the way that AI is currently being built which has that kind of human compatibility built into it, right? The two things that I think are properties of the way in which AI systems are currently trained that do contribute to this to some extent are, first of all, training on language, right? Or other data which are human-generated data. That's something which means that these systems end up kind of like viewing the world in the same way that we do, because they're viewing it through the lens that we provided, right? So if you think about what language is doing, language is one of those mechanisms that humans developed as a means of overcoming that limited communication bottleneck. And as a consequence, it's a thing that we use to describe the world around us in a very compressed form. And so that compressed form, as well as the structure of language itself, is something which, when you put it into an AI system, means that that system actually gets a lot of knowledge about the world that's being digested through human minds, right? And so that's one thing that maybe stops these systems from being quite as alien as they could be, is that they are really sort of like trained to view the world in the same way that a human has. The other thing is the last stage of training for many AI models is something called reinforcement learning from human feedback, right? RLHF. And that's something where humans give direct information about the preferences that they have about the responses that a system is producing. And that's something which in some ways contributes to alignment between humans and machines, although we have a recent paper where we argue that, in fact, what it results in is more alignment between the current state of knowledge that humans have and machines, right, which is not necessarily the same thing as having the human's best interests in mind as you go further into the future. And you can think about this even in simple examples, like if you're building a chatbot that is going to advise you on what products to purchase, unless that chatbot is receiving its reinforcement based on how satisfied you are with the product, after you've bought it, right, then it's going to be incentivized to instead focus on giving you the information that makes you satisfied at the point where you make the purchase. And that is not the same thing. And it's not the same thing in a way that can, lead those models to intentionally, well, we shouldn't say intentionally because it's not a intentional agent, but to engage in behavior that, a human being would consider deceptive. And so I think if you really want to build systems that are designed to interact with people, then there's a lot more things that we could do which are making direct use of the things that we know about people. So we've done a bunch of work on what we call representational alignment, which is making sure that the representations that the models have are the same as the representations that humans have. And so in some early work, we actually showed that if you train a vision model on, instead of training it on sort of sanitized data, where every image has a label which is the sort of agreed upon label that the humans give it. If you train those models instead on data that contains human errors, where when the humans are confused, you include those labels too, the models actually end up with better representations and representations that are more aligned with those of people. So that's something where having this more complete information about how humans see the world and the kinds of things that humans find confusing actually lets the model get representations that are more human-like. And in other work, we've shown that models that have more human-like representations actually do a better job at things like learning from small amounts of data and at learning to capture human moral judgments, right? So if you view the world in the same way, that gives you a better basis for being able to feel the same way about the world in terms of what's a good action to take versus a bad action to take. And we've done other work where we talk about a more general idea of conceptual alignment, which goes beyond just sort of having these representations that we can measure in terms of what's inside the model that align, and really being focused on this notion of like understanding the world in terms of the same basic concepts. And so even when we have models that sort of correlate in their representations, they can still be quite different in the way they're making sense of the world. So for example, humans think about the world in a way where we distinguish between different numbers of objects, right? Where the number of things is the sort of discrete thing that we represent and we can individuate. And it seems like, at least if you take image models, once you get past 4 or 5 or 6 objects in an image, they kind of lose track of what those numbers are. So they just sort of have, like maybe have somewhat individuated representations of small numbers, but they just have sort of like a fuzzy mass when you when you get beyond those small numbers. And that's exactly how part of human cognition works, right? If I show you an image and I ask you how many things are in it, if there's up to 4 things in the image, you're going to be able to answer it perfectly, and then after that you drop off. But we have this other richer conceptual representation which allows us to individuate higher numbers, 30 and 31 from each other and so on. And so at the moment, our AI systems are capturing sort of part of how humans perceive the world. It's kind of like the part that happens very quickly. that you're able to do in, less than a second, where you're just sort of like seeing something and making sense of it, or sort of like, reading something and getting the gist of it. But they're missing something, which is the more symbolic, abstract representations that people form. And so we have a paper called Machines That Learn and Think with People, where we make this argument. And so to say, if you really want to make machines that are able to engage with humans in all the ways that humans engage with humans, then we need to capture more of the kind of thing that allows humans to engage with humans, which is having these shared representations of the world. And that's probably going to require some innovation in terms of the methods that we use for building these AI systems.
Yeah, okay, that's so fascinating. And I'm curious. So my main, one of my main questions in these is, how can we apply what we learned basically so far about human biases and cognition to make these generative AI assistants basically elevate us and help us try and not fall into these biases that may be conscious and unconscious, but we know about them from research. How can we make that happen? Because what I'm thinking is, if we're trying to make them to our perfect image and symmetry, that's useful, but I think we would be missing one of the most interesting parts, which is trying to make us better humans instead of just the same we are. And so, is that possible? Is that something the research is currently going towards? How hard is it? It's like it seems like a huge endeavor to me.
Yeah, I mean, my first response would be, for the reasons that I said, it's not clear to me that an objective should be building AI systems that are like people, because people, like, I agree. What human minds are is a consequence of this evolutionary process, right? That reflected various biological constraints that we operate under, and it might be better to think about it in terms of, what's the best way for us to build intelligent systems that aren't like people, in terms of what's easy for us to engineer, but also something that's easy for people to interact with, right? And I think that's a perfectly reasonable goal for AI, right? So, if you think about, birds and jet planes, which is an example that people who work on AI talk about a fair amount, right? So, studying how birds fly is incredibly important to making your first airplane, right? In terms of like understanding aerodynamics and lift and all of these fundamental concepts that are intrinsic to like how you're going to design the wings of your plane and sort of figure out like what it is that actually makes something fly. But there's a point where once you have something that's flying, you can engage in an iterative process, which is the one that leads you to jet planes, right? And jet planes and birds are very different from one another. And I think that's a totally reasonable place to end up, right? I'm not going to be someone who's going to be like, we should build flying machines that are more like birds. There are plenty of reasons why, you might want to take some more bird-like properties and put them into jet planes. For example, being more efficient in their fuel consumption, or other kinds of characteristics that birds have. Birds are sort of amazing as examples of flying machines, right? But it's not something that, if your fundamental goal is, I want to get from one location to another as fast as possible, that's something where, like learning more about like jet engines is probably the way to go, right? And I sort of feel like we're in the same space with AI. It's like, yes, there's plenty of things that we can still learn from human cognition, but we shouldn't, say that our objective is to build something which is, human-like necessarily. So that said, there are plenty of ways that AI can be helpful to humans. So one of the things that I work on is understanding human decision making, and this kind of goes back to those experiments by Kahneman and Tversky that I talked about before, right? So part of what they showed was that not just people are bad at reasoning about probabilities, but people are bad at making decisions with respect to expected utility theory as our kind of criterion of what it means to be a good decision maker. And That's certainly true. And if we try and think about that in terms of the different levels of analysis, right? Expected utility theory is our abstract computational level theory. It tells us what we should be doing. But there's a sense in which that is a kind of theory which, in fact, could not be achieved by any real entity that exists in the world, right? So expected utility theory says no matter how many outcomes you have, for each of those outcomes, evaluate the utility, evaluate the probability, take the expectation. If you're trying to use that as a guide to making any real decision, it's kind of impossible to do that, right? Because you'll just spend your entire life thinking about possible outcomes, trying to evaluate how good they are, trying to evaluate how probable they are. And in fact, most of the time when we have to make a decision, we have to do it under some kind of time constraints. And so those constraints are things that are intrinsic to the way that the problem is set up. They're also a consequence of that sort of second level with the kinds of algorithms that we're able to execute on our human brains, right? And that sort of gets us down to the third level. So it's, things from these other levels of analysis that are influencing the problem that we should be thinking about. And so back in the 1980s, some computer scientists who are trying to figure out how to make a good AI system, this is like Stuart Russell and Eric Horvitz, among others, they tried to work out, well, what's actually the right optimization problem to set up for making a decision? And they came up with an idea that they call bounded optimality. Basically, the idea is that a bounded optimal agent is one that uses the best possible algorithm for making a decision, taking into account not just the outcomes that produces, the sort of expected value of those outcomes, but also the computational cost involved in executing that algorithm. And that's a much more realistic way of thinking about how to characterize optimal decision making. We've used that idea and expanded on it in an approach that we call resource rationality, which is the idea that actually being a rational agent means making rational use of the limited cognitive resources that you have to do the best that you can in making the decisions that you make. And we can use that as a lens for then going back and reevaluating human decisions. And when you do that, you find out that a lot of the things that people do that deviate from expected utility theory are actually things that kind of make sense from the perspective of resource rationality. Like the heuristics that people use for solving problems are typically good heuristics when evaluated by this criterion of, do they, achieve relatively high expected utility while, not incurring too much computational cost. But the other thing that you get out of this is a perspective on how you can help humans make better decisions, which is that if we're making bad decisions some of the time because of those resource constraints, one way that we can better support human decision making is by increasing the computational resources that are available to human agents. And so, Elon Musk is trying to do that by putting chips in people's brains. That's not where we are in this space. Instead, what we focused on is, what if you can use AI systems to put more compute in human environments, right? So that when you are making a decision, we've sort of partially pre-solved part of that problem, and we can give you information in a much more accessible way that's going to help you make a good decision. So either putting the most relevant information in the most easily accessible place, or giving you information about payoffs that supplements, the information that's immediately available to you, sort of gamification, right? Where we're saying, you get some more points if you, choose this option, right? Where you can actually set up those points in a way that better aligns with people's long-term goals, right? Like one of my collaborators, Falk Leader, has worked on making gamified to-do lists where you can specify the things that you want to do and how valuable they are, and sort of break these down into components, and then it sort of automatically works out how many points you should get for doing each thing. And that gives you a kind of much more immediate reward for like checking something off your to-do list as those points add up, and maybe you get yourself, some prize when you get enough points. And that's a way of sort of like helping to motivate humans who, might not be able to plan all the way to the end of some long-term goals. And we've actually run experiments. We've shown that this kind of thing can help people reduce procrastination. So those are ways of using elements of AI systems to help humans without having to go all the way to like building something which is, a human-like AI.
I love that. Damn, this, Absolutely fascinating. I have still so many questions for you. I know, well, I'll start winding us down because I don't want to take 3 hours of your time. But something I'm also curious, and I think you also work on that, is the language learning aspect of these generative AI models. Yeah, can you talk a bit about that? How does that work? How do you make an AI learn language and grammar? If I understood correctly, grammar is something that's quite hard. So yeah, what's the state of the art right now, and how does this work?
Yeah, so the basic principle behind the large language models that are used in current AI systems is a very nice statistical principle, which is the goal of these systems is, based on the words that you've seen in a document so far, predict the next word that'll appear in that document, right? It's a very simple kind of objective to define. And this is called autoregression, right? By analogy to more familiar autoregressive models that you might use for time series analysis. That idea itself goes back to cognitive science. A cognitive scientist named Jeff Ellman published a paper in 1990 where he showed that using that kind of objective was actually an effective way of learning, in his case, a very simple language. So he sort of made up a simple language. That simple language, he trained his neural network on what now seems kind of quaint. It's like 10,000 words that were generated in that simple language. And he showed that when he analyzed what the neural network had learned, it had actually pulled out things like nouns and verbs, and the fact that there are different kinds of nouns and different kinds of verbs that interact with one another in different ways. So it had kind of like pulled out this information in the hidden units of that model, right? The representations that the model had formed. It had made distinctions between these different syntactic classes that were key to the simple language that he'd created. And so, honestly, the story of creating the modern large language models is essentially a story of scaling that up, right? So it's increasing the amount of data that the models are trained on, and also modifying the architectures of the neural networks which are used for solving those problems. So Ellman's original model used something called a simple recurrent network, which would just sort of copy some of the information that it had used to predict the last word, and then have that information available when it's predicting the next word. So it copied those internal hidden unit states. And that works fine for learning short sequences, but as you start to try and learn long sequences, it runs into all sorts of problems just as a consequence of the dynamics of, like basically you start losing information very quickly when you're engaging in that copying process for reasons that are related to the iterated learning thing that I was talking about before. It's just like any iterated process, you can potentially it's hard to carry information forward. And so there was another innovation called long short-term memory networks, which were basically a way of allowing the neural network to make decisions about what information it would store in memory and what information it would read out. And then those were used to significantly, expand what these kinds of neural network models could learn. And then the latest generation of these models uses an architecture that's called the transformer architecture. And in that architecture, instead of processing words one by one and making the prediction about the next word, it has the whole sequence available to it when it's making that prediction. And what it learns is what words within that sequence it should be paying attention to in order to generate that prediction in a way that, is then sort of able to change dynamically for whatever sequences it's looking at. And that's a very powerful way of, it's not necessarily particularly human-like. Again, sort of making this difference between the engineered system and the human system, right? You as a human pretty much have to process stuff in real time. Whereas the model is able to kind of look back and forth, and it's able to look along the entire sequence when it's making that prediction. So it's much more like if I gave you a written document and I asked you to predict the next word, and you could be going back and looking at all of the words in that document and sort of circling them and figuring out which ones you're going to use to then make that prediction about what that next word is going to be. And that architecture is even more effective. And that's the architecture that modern large language models are based on. So alongside those architectural innovations, you just have massive increases in the amount of data that are being supplied to the systems, where GPT-3, which is the last of the OpenAI models that we know, a reasonable amount about what it was actually trained on. It was trained on the equivalent of, if you just had somebody reading out the training data, it would be 5,000 years of continuous speech, right? So like go back to ancient Egypt, start reading 24 hours a day. You would stop now. That is the data that it'll learn from. And then the models that are successors to that have been trained on, again, like another order of magnitude more data. And so really it's those two things. And I think the surprise for many cognitive scientists is that that's enough. You can get to a remarkably complete understanding of language, given those neural network architectures and enough training data.
Yeah, that sounds like an awesome project, but also like huge endeavor. And I'm wondering also, now that we talk about a bit how you see these next project in the future, I'm also wondering, how do you see the future of Bayesian methods in cognitive science for this kind of work that you're doing and talking about right now?
Yeah. I mean, so I think this case is actually a really good one for highlighting what's different between humans and these machines, right? So, okay, take that GPT-3 case. Does a remarkably good job of learning, like not just English, but multiple languages, right? From 5,000 years of data. Okay, take the human being, does a pretty good job of learning language from, 5 years of data, actually less than 5, because my number was speaking 24 hours a day, and kids do not get spoken to 24 hours a day, right? But there's like at least 3 orders of magnitude difference in the amount of data that humans are using to achieve the state that they get to. And so when you think about that in terms of solving an inductive problem, the only place where that missing piece can come from, right, that allows you to get to that level of performance with so much less data is inductive bias, the kind of thing that in a Bayesian framework we would express in terms of like a prior distribution, right? So one way of thinking about that is humans have some prior distribution over languages that's much more informative than the implicit prior distribution, which is built into a transformer model. And so that's part of the project of a cognitive scientist, is to figure out what is that distribution like, right? Like what is that the way to characterize those human inductive biases for language learning. And that's a huge project. It's the kind of thing that linguists have been engaged in for the last 70 years at least, in terms of like looking across different human languages, looking at the things that people can learn. We've used methods like the iterated learning method that I talked about as a way to reveal some aspects of what those human prior distributions for learning languages look like. We've also used a method called meta-learning as a way of exploring this. So you can kind of turn this problem around and you can say, if I took the data that kids get exposed to from different human languages, can I reverse engineer what inductive bias you would need to have in order to be able to learn to speak those languages? And you can do this using a tool that's come from the machine learning community called meta-learning, which is basically you have a training procedure where you're going to train a bunch of neural networks to perform different tasks, but all of those neural networks are going to have the same initial weights. And so you then have an inner loop where they learn to perform the tasks, and an outer loop where you optimize the initial weights. And the initial weights of a neural network are one way of, that's one factor that influences the inductive bias of that network. So you can think about what that's doing is it's trying to find a sort of starting point in weight space so that by doing your neural network learning from that starting point, you're going to end up at the endpoints that you want to get to. And so we can use that actually as a tool for trying to work out what's a good starting point, what's a good set of initial weights for characterizing what you might need to have in order to be able to learn the things that humans learn from the data that humans actually get exposed to. And we have a paper where we show that, in fact, that method is a kind of hierarchical Bayesian method. So you can show that this is exact in the case where these are linear models that you're optimizing, and it's a little more heuristic in the case of neural networks. But that's a way to think about it, is that it's a way of like trying to back out a prior distribution expressed in terms of the weights of a neural network. And so I think there's all sorts of interesting things for cognitive scientists to do in, this world where one of the challenges that AI faces at the moment, and, we'll see how much of a challenge this is ultimately, but they're starting to run out of data. So, the models have been trained on, all human-generated text in electronic form. And so the question is, where do they go next to make the models better? One way to go is to try and understand what those human inductive biases are like and think about how you can implement something like that in these models. That's certainly a direction that I'm excited about. I think the other way that we can use these cognitive scientists' tools are understanding more about the actual inductive biases that these models have, understanding how they relate to or differ from human inductive biases, and just getting a better sense of what the capacities of these models are. Because one of the challenges of working with these kinds of neural network models that underlie most of modern AI is that they're really opaque, right? It's really hard to know what assumptions they're making. So part of what attracts me to Bayesian statistics is we know exactly what assumptions we're making. We write them down, and then we derive their consequences. And so the more we can do to characterize for these neural networks what they're doing in something like Bayesian terms, the better position it puts us in order to think about, what the consequences might be of deploying them in a particular situation, what's the right kind of model to use in a particular situation, how are these models different from the assumptions humans might make, things that are actually relevant to thinking about, how do we guarantee better outcomes from deploying these models?
Yeah, it's so many interesting things in your agenda, I guess, for that coming year and in the many years to come, I'm guessing. And actually, so you're not only a researcher, right? You're also a director of a lab. So I'm guessing you also see a lot of students. You even mentor some PhD students. I'm wondering what advice you would give to someone starting out right now in Bayesian stats and or cognitive science, and someone who is interested in what you're doing and would like to do it too?
Yeah, I think one thing that happened when ChatGPT came out was that a lot of my students who work on Bayesian methods were kind of worried at that point, right? I did a lot of counseling of graduate students where I think there was a concern that whatever problem they were working on was going to be solved by some relatively dumb machine learning method scaling up, right? Or just, or by the systems that are created as a consequence of that process. And B, that they might not be able to get jobs because people might not be interested in hiring people who are working on Bayesian methods. They might just want to hire people who are working on deep learning or large language models or whatever it is. So I think for anyone who's in this space, my advice is I think you should work on the things that you're interested in, right? Like if you're drawn to Bayesian methods, work on Bayesian methods. But with two caveats. So one of those is it's better to work on a problem than a method, right? So it's better to say, this is the thing that I want to understand, or this is the problem that I want to solve, than to say, I am going to solve this problem using Markov chain Monte Carlo or whatever it is, right? Because if you have a problem, somebody making progress on methods is good news for you, right? So as AI gets better, you're putting yourself in a position to do a better job of solving your problem, rather than worrying about, someone is going to, do something which is better than the method that I'm using. And so choosing to structure your research program in a way where improvements in AI are positive outcomes for you rather than negative outcomes is a really important thing to think about at the moment, just because stuff is happening so fast, right? So that's thing number one. And thing number two is, I think just strategically, whatever you're working on, it's good to think about how to relate that to these kinds of developments, right? So it doesn't have to be that you make your research program all about large language models, but it's quite helpful if you have one paper where you think about large language models or deep learning or whatever it is and how it relates to the problem that you're solving, because that's a way of communicating that these methods as well, and that you're able to talk about them intelligently. If you're looking for academic jobs, you're able to teach a class on those methods, and that the questions and methods that you work on aren't going to be things that are going to be superseded, but they're things that are compatible with whatever those new approaches are. And so those two principles are things that I use when I'm, sort of mentoring students and guiding them and thinking about their research programs and choosing projects, just to, position yourself to succeed and be able to communicate how it is that the things that you work on are relevant to all of these exciting things that are happening in modern AI.
Okay, so mainly focusing on solving the problems, not really on the methods.
Yeah, I mean, that's something where I think building a strong methodological toolbox puts you in a good position to be able to, roll with the punches, right? But it's that you shouldn't be committed to the idea that one particular method is going to be the thing which is what you're going to be focused on for your whole career, certainly, but maybe even not for the next few years. And there are plenty of examples of this, like I mentioned our crazy experiments where we run Markov chain Monte Carlo algorithms with people. We also run those crazy Markov chain Monte Carlo algorithms on large language models, right? And it's Markov chain Monte Carlo, but we're using it in weird ways that are responsive to the particular problems or questions that come up in different disciplines. And I think being able to be creative, like I still continue to think that Bayesian statistics is a fundamental, incredibly valuable toolkit for anyone who's doing research on AI, machine learning, cognitive science, precisely because it tells us what optimal solutions to problems look like, right? And if any kind of system is doing a good job of solving a problem, it's going to be doing something which is, approximating what those optimal solutions are. And a lot of research which is done in AI and machine learning is, often done in a kind of like, I put these things together and it works kind of way at the moment. And so being somebody who has that toolkit to be able to come in and say, this is why it works, this is where it's not going to work, and this is a solution to that problem, that is super useful. And, it's a very powerful way of being able to engage with, this like huge amount of research which is going on. And so for me, those are the papers that I find most satisfying, are the ones where we're able to take something that's relatively ad hoc, explain it, extend it, improve upon it. That's the stuff that gets me most excited in research.
Yeah. And so concretely, actually, what did you recommend your students, who were worried that their investment in these hard methods, because the problem is that, learning new I get the advice of, being flexible with the methods you use and so on is, important. And in a world where it would be easy to learn methods, so for instance, if you were like in the Matrix and you just put, you just have to watch a tape and then something, well, the most rational thing to do would be to just jump methods all the time you need. In our world, though, in the way we learn, it's not possible, especially since the methods we use for inference are definitely complex, and you acquire them with months, if not years, of training. So changing is not like if you're on a small boat, you cannot turn very fast. It's more like you're on a cruise ship and it takes time to do a U-turn. So like in these cases, I'm wondering what the optimal decision would be for these kind of students, where like, well, actually the methods you learned is still extremely valuable, and I would still work with that, or no, you need to change something right now. How do you handle these cases?
I think if you're very invested in the methods, then the right strategy is one of like looking to the contemporary machine learning literature and looking for places where those methods can be used to answer questions in that literature, right? And that's much more straightforward. And it doesn't have to be the thing that is like, your core interest in questions can be the core interest in questions that you have. But I think it's more being open to finding those opportunities, and like I said, like communicating with that literature, right? And think there are lots of good ways to do that in terms of, places where, for the reasons I outlined, like thinking about these systems from the perspective of Bayesian statistics is a very rich lens to use in trying to make sense of them. And it's a skill set that's rare, right? At this point, like 90+% of the research that's being done in machine learning at the moment is probably being done by people who don't have a deep, grounding in those kinds of Bayesian methods, and so that's a competitive advantage. And so, I think the one thing I would sort of discourage is just sort of being dogmatic about it, right? Saying, "Oh, I don't do that kind of thing. I do this Bayesian stuff," because I think that's something where you can just shut yourself in a box. I think it's, being able to be responsive and open to these things and think about them, and there are plenty of ways that you can get communication going back and forth between these different fields.
Yeah, I agree. That makes sense. And actually, what do you think are the most promising trends or advancement in your field that you would recommend such a student or a professional to invest in, like someone who knows already, like your students, well, the Bayesian methods, but you see some advancement in other methods or other tools that you would recommend these people to learn because this would be a good investment of their time?
I mean, I actually think the thing I would recommend, and this is, somewhat self-centered perspective, right? But is, some of the papers that we write are really about, like, how do you take a Bayesian view of these things? And in some ways that's most useful because it's building a bridge, right? And that bridge allows you to make use of the methods that you already know, right? Where if you can say, oh, okay, here's a set of things that here's this, other set of things, and now I can tell you, oh, that thing is relevant to this thing, and that thing's relevant to this thing, and that thing's relevant to this thing. That gives you a little bit of a map of the territory that you can explore. So we have a paper called Bayes in the Age of Intelligent Machines, where we make this argument that Bayesian reasoning is really relevant to building AI systems. There's a nice position paper that was at ICML last year. I think if you just Google position deep learning, that's a paper that's really a good summary of the state of the art in Bayesian thinking as applied to machine learning models. And then our paper, Embers of Autoregression, is a characterization of like large language models from this Bayesian perspective, and cites some related things. There's also a lot of nice work on like in-context learning in large language models as Bayesian inference. Some of that work has come out of Percy Liang's group, and we cite some of that work. But those are places to look for, sort of like nice connections between Bayes and contemporary machine learning methods.
Yeah, definitely feel free to add these links to the show notes, because I think lots of people will be interested in that and want to dig deeper. Okay, so that's already being a long time. I have to let you go in a few minutes. So let me ask you one last question before the last two questions. Mainly about you. Yeah, what's next for you? Are there any upcoming projects or ideas you're particularly excited about for the next coming month?
I mean, in general, I think this is a super exciting time to be a cognitive scientist, right? For a long time, we only had one really intelligent system to study, and now we have a bunch, and that's creating all sorts of fun opportunities. We've been doing a lot of LLM psychology, like trying to make sense of what's going on in large language models and related models. And that's a fun way to use as I said, like a toolbox that's coming from another discipline and applying it in the context of AI. The other kinds of things that I do in my lab are these really large-scale studies of decision-making, and we have a few of these things that are coming together and going to be exciting papers that I'm looking forward to working on. Other than that, my main job at the moment is we just started a new AI lab at Princeton, which is a big interdisciplinary effort to explore how AI can be used to support research across the entire university, ultimately, and to try and figure out how do we, support AI research on campus more generally. So I'm the director of that effort. That's been taking a lot of time and is at the point where it's really starting to accelerate, and that's super exciting. Like the thing that I see here is the potential transformative impact of AI across many different disciplines where, for example, the Nobel Prize in Chemistry this year, that's just one indicator of, I think, what's going to come, which is as these methods propagate out across all of the different research disciplines, they're going to enable us to make discoveries that we couldn't have made before. And I'm excited to be part of that process at Princeton.
Awesome. Well, Tom, that was an absolute pleasure to have you on the show. And well, before you go, of course, I'm going to ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
I think a really deep, interesting problem at the moment is figuring out how to scale Bayesian inference. Right. So you can think about a lot of the success of the current AI paradigm as a consequence of people kind of figuring out how to scale neural networks, better methods for doing backpropagation, automatic differentiation, things to stop gradients disappearing in deeper networks. These were all insights that made it possible to create bigger and bigger neural networks, and that was crucial to then being able to then train models that could work at, with these very large data sets. Bayes is even more notorious for having problems with scale. But I'm really curious about what happens when we scale Bayes in the same way that we've been able to scale these other kinds of methods. So that's a huge challenge, but it's, as you said, unlimited time and resources. That's the one I would pick.
And if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I assume that they're alive at the point where you're eating dinner with them, right? Because
right.
Otherwise it would be boring dinner. One of my intellectual heroes is Leibniz. I think that would be fun, just because, he's somebody who was just like all over all sorts of ideas that have been incredibly fundamental ideas to not just cognitive science, but, all sorts of other disciplines. He's not in our normal Bayesian pantheon, but he was actually very interested in probability, right? He did his early work was on combinatorics, and he started to think about probability and started to even think about it in terms of, being an extension to the kind of basic methods of logic that he was starting to think about. So definitely somebody I would enjoy having dinner with.
Yeah. Yeah, it's a great answer. I think nobody gave that yet, but I'm surprised because Leibniz is definitely a big name of science, and not only statistics but math and physics. So it's definitely sounds like a great dinner, Tom. Well, amazing. Thank you so much for taking the time, Tom. That was absolutely incredible. I still have so many questions for you, but I definitely recommend your new book to listeners. This will be in the show notes. There will be also other links that Tom mentioned to some papers. So all of these will be in the show notes for those who want to dig deeper. Thank you again, Tom, for taking the time and being on this show.
Thanks for having me. Maybe I can answer the other questions next time I write a book.
Oh yeah, for sure. Okay, come back next time you have a book. You're all welcome to come, and that will be very fun.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.